LLMs like ChatGPT, Claude, DeepSeek, Grok, and Gemini. SLMs like Phi, Gamma, and Qwen, as well as agentic AI systems which will power the future of the labor industry. At first glance, they all seem different. Different companies, different products, different goals. But if we peek under the hood, they all share one common foundation. That foundation is a transformer architecture. Introduced by Google in 2017, this single architecture has powered almost every breakthrough in generative AI over the last decade. At first, it was a research curiosity, a clever idea in a paper that only a few experts noticed. But then, something incredible happened. In 2022, OpenAI released ChatGPT. Overnight, the world discovered what transformers could really do. Suddenly, a model could understand and generate human-like text. Soon after, other companies followed. Claude, Gemini, Grok, all built on the same transformer foundation. And it wasn't just language, vision, speech, and now decision-making AI agents all rely on the same architecture to power their intelligence. To give you an analogy, imagine if there was a single engine that sits under the hood of all different car models. Sedans, SUVs, sports cars. Each vehicle looks different, drives differently, and serves a different purpose. But the engine is still the same. That is a transformer, the engine that powers modern generative AI. Over the years, this architecture became the backbone of innovation.
Artificial intelligence is making rapid strides.
ChatGPT revolutionized conversational AI. Gemini transformed creative image generation. Autonomous agentic AI systems streamline tasks that require decision-making. In less than a decade, the transformer went from a research paper to the foundation of millions of AI applications across the globe. Yet, despite all its success, this engine, as powerful as it is, has fundamental limitations. Limitations that still handicap all generative AI models today. The transformer changed the world, but as every engine, it has its own limits. The first and most obvious limitation of transformer-based generative models is what AI engineers call its black box nature. Generative models work. They answer questions, they generate text, and they make decisions. But there's one unsettling truth. The internal processes and functions in these models are mostly unreadable to humans. This issue isn't new. It has existed since the early days of artificial neural networks. All AI engineers know that LLMs are and continue to be black boxes. You give them an input, they give you an output. What happens in between is largely invisible. There is an entire field of research dedicated to uncovering this mystery, that is mechanistic interpretability. The goal is simple in theory. Take a model apart and link its internal components, neurons, weights, activations to clear, human, understandable concepts. But in practice, it has failed. After years of work, researchers have only managed to interpret a tiny fraction of large language models, less than 1% of their internal structure. The remaining 99% unmapped, unexplained, not for a lack of effort, but because by design, they are inherently unintelligible. That's why AI researchers call it the dark matter of AI. Why this happens? In the human brain, specific neurons specialize. In generative models, they don't. Concepts aren't stored in one place, they are smeared across millions and sometimes billions of parameters and nodes. This happens because of the learning algorithm itself. At its core, it's a glorified form of curve fitting. The result? No single neuron means anything by itself. No single weight represents a clear feature. Thoughts are diffuse, memory is entangled, meaning is scattered. This leads to two serious problems. First, you can never internally trace why a model produced a specific answer. And second, auditing, debugging, and even correcting behavior becomes nearly impossible. In high-stakes systems like medicine, finance, and defense, that's not just inconvenient, it's a safety hazard. A recent MIT study revealed something even more disturbing. The researchers asked the model a simple question: where is Paris located? The model answered correctly, France. Then they asked the second question, one that makes no sense at all. Quickly said Paris clouded. The model answered France. Why, they figured? The model just recognized a pattern, adverb followed by a verb followed by an entity, and that pattern triggered a memorized response, while ignoring the semantic incoherence of the question. Models take so many such shortcuts that hide unnoticed, and these causes all forms of adversarial vulnerabilities. Attackers can exploit it, safeguards can be bypassed, behavior can be manipulated. The second problem these models face is data inefficiency. Transformer-based models don't just need data, they devour data. Public estimates suggest that training GPT-5 required on the order of 40 trillion tokens. To put that into perspective, an average page of text contains about 500 words, which translates to around 700 tokens. That means GPT-5 consumed the equivalent of 60 billion pages, or roughly 240 million books. That's twice the number of books ever written in human history. And the catch? Much of that data isn't unique. Data samples are duplicated hundreds and even thousands of times. Why? Because transformers suffer from some disease called catastrophic forgetting. When new data is learned, it overwrites old knowledge because everything is stored in the same tangled parameters. To compensate, the same information must be shown to the model hundreds or thousands of times. This means what can be learned using 10 million data samples, current models achieve using up to 10 billion of these samples. The third problem is compute. The amount of computational requirement to train modern LLMs is staggering. Estimates for GPT-5 range from tens of millions to nearly 100 million exaflops. For context, 1 exaflop equals 1 million trillion operations per second. To put this into perspective, the most powerful supercomputer on Earth, El Capitan, delivers about 2 exaflops. At that speed, it would need to run for months to train a single model, and that's of course assuming perfect efficiency. This level of compute intensity takes us to the next problem: energy. AI data centers now consume city-level amount of electricity. You probably heard about this in the news before, how AI strain power grids and drive up energy costs. The main culprit is GPUs, some of the most power-hungry components in modern computing. You see, training and deploying AI-generative models rely heavily on a massive network of power-hungry GPUs. This mirrors the energy dynamics of cryptocurrency mining, which also uses GPUs, and which causes intensive energy demands to the point that multiple countries had to ban crypto mining altogether. But unlike crypto mining, AI isn't optional, it's becoming foundational. And that means this isn't just a technical issue anymore, it's an economic problem, an environmental problem, and increasingly, a geopolitical one. From the outside, it looks like an arms race. Every few months, a new model, a new name, a new benchmark shattered. But behind the scenes, something far less revolutionary is happening. The transformer architecture was introduced in 2017, and despite everything you have seen since, every breakthrough headline, every product launch, every viral demo, everyone is still using that same foundation. The core design hasn't changed. Over the past 5 years, AI companies haven't replaced the transformer, they have patched it. You see, each company added its own tweaks, small optimizations, clever tricks, mathematical band-aids. Each patch brought a little more performance, a little more scale, a little more runway. So let me quickly walk you through the most important ones. The first major breakthrough was brutally simple. More data gets you better performance, and better quality data also gets you better performance. After all, garbage in, garbage out, right? This realization triggered the era of massive dataset collection, filtering, and curation. Then came scaling laws. Researchers discovered that bigger models with more parameters generally perform better, but only if data grows with them. This led to compute optimal ratios, most famously the chinchilla rule, 20 training tokens per parameter. Models got deeper, aka more layers, models got wider, aka more attention heads. Simply, performance improved by making the engine bigger.
Next came alignment. Models didn't just need to predict text, they needed to generate response and behave in certain ways for different tasks. So companies introduced SFT, supervised fine-tuning, RLVR, reinforcement learning with verifiable rewards, RLHF, reinforcement learning with human feedback, DPO, direct preference optimization, among many. To put it in simple terms, AI companies began hiring domain experts, translators, doctors, lawyers, educators, to curate data and guide model behavior within their specific domains. In other words, humans teaching the model how humans prefer answers to sound in different situations. This made models safer, more polite, and more useful. Then mixture of experts arrived. Simply, different parts of the network specialize on different domains of knowledge. Each subnetwork acts as an expert and specializes. And when generating a response, instead of activating the entire network every time, only the relevant specialized subnetworks turn on. The result? Lower compute per token, better specialization, but the core engine remained the same. Some improvements focused on inference, for example context caching, which includes KV cache reuse introduced in late 2024 by DeepSeek. Put it simply, the idea is that we don't have to recompute the full attention pattern for every response generation step. Instead, we can store intermediate values in cache memory. This cut latency and reduced inference cost. Then come chain of thought, originally proposed by Google Brain in 2022, but made famous in 2025 with DeepSeek's R1 model. The idea was simple: force the model to think out loud by fine-tuning it with datasets that are structured as step-by-step answers, and by rewarding the model when producing intermediate chain of reason. The result? A model that starts reasoning step-by-step in plain English. As models grew deeper, they became unstable, so in 2026 DeepSeek introduced manifold constrained hyperconnections. To give you an intuitive understanding, a model is composed of many deep layers. Those layers are connected by bridges called residual connections. Traditional residual connections were unconstrained and chaotic, creating numerous unstable paths for learning signal to flow. DeepSeek's manifold constrained hyperconnections imposed a form of structure on these paths, which guide learning signals more efficiently, enabling stable training at unprecedented model depth. A brilliant fix, but still a fix. Another patch emerged in 2026, recursive prompting and recursive language models. Instead of feeding a long prompt directly into the model's fixed context window, an RLM places the entire context as a variable within an execution environment. The model then interacts with this data by writing and running code. This enables effective context window sizes of millions of tokens. Traditional transformer models process reasoning and knowledge retrieval through the same network, whether it's thinking or remembering. DeepSeek proposed something different. Instead of forcing the model to store everything inside its weights, it introduced a conditional memory. Attention computes a context-dependent embedding, the model's current thought. That thought is then used to query a memory system, retrieving only a small relevant subset of stored representations. In principle, it's simple. For a given thought, the model performs a fast lookup in a separate database rather than activating the entire network. Despite their impact, all of these advances are fundamentally patches. They don't address the core flaw of the architecture which power all these generative AI models. Most performance gains still arise from scaling data, scaling parameters, and scaling compute. Additionally, they help models scale further before hitting plateaus, but they do not change why those plateaus exist in the first place. So despite all these patches, the core architecture design remains unchanged, and so do the problems: compute inefficiency, massive data redundancy, escalating energy demand, and black box reasoning. These aren't bugs, they are consequences of the architecture itself. AI companies are competing with one another left and right by introducing their own novel patches to the same old engine. But what if the old engine itself needs to change? For nearly a decade, the world of AI has been moving faster and faster, but always along the same track: more data, more parameters, more compute. So we asked a different question: what if we change that track? At SilicoSapien, we introduced a neuromorphic symbolic transformer. Not a patch, not an optimization, but a fundamentally new engine for generative AI, designed from the ground up to overcome the core limitations of the traditional transformer. To understand how it differs, let's run a simple thought experiment. Imagine two classrooms with two teachers, each trying to teach the same lesson through two different teaching methods. In the first room, students are never taught. they are tested immediately. For every wrong answer, they are punished. The more wrong the answer, the harsher the punishment. Most students fail badly. A few do slightly better by chance. Then they take another test, again and again and again. Over time, students don't necessarily learn the lesson, they learn how to avoid punishment. They guess patterns, they memorize shortcuts, they minimize pain by minimizing answering incorrectly. This is how traditional transformer models learn. Learning is driven by punishment minimization, effective at scale, but slow, inefficient, and opaque. Now the second rule. Here the teacher explains the lesson first. Concepts are explained, relationships are built, ideas are associated. Only then does testing begin. Correct answers are rewarded, wrong answers are corrected. The result? Students learn faster, they need fewer tests, they understand the material better. This classroom mirrors how biological intelligence learns, and it mirrors how our architecture learns. The neuromorphic symbolic transformer integrates three learning mechanisms known to operate in the human brain. First, Hebbian associative learning, features that core become linked, neurons that fire together wire together. Second, neural selectivity, neurons specialize, meaning becomes localized, not smeared. And third, localized cross-entropy reinforcement, prediction surprise triggers targeted reward or correction, as opposed to global parameter reshaping. SilicoSapien is the first organization to integrate all three mechanisms inside a scalable, transformer-like, context-aware generative architecture. Despite years of effort across the industry, no prior system achieved this, because traditional transformers simply weren't built for it. This single breakthrough unlocks everything that follows. A synapse represents one feature, a neuron represents one context-dependent concept. Learning signals are localized. As a result, concepts are no longer diffused across billions of parameters. Every decision can be traced end-to-end. Biases can be inspected, failures can be corrected at the source. No need for post hoc explanations, no longer doing approximations. Transparency is inherent to the design. This is unprecedented, the only architecture in the world that supports white box fully transparent generative models, aka the holy grail of AI interpretability. What interpretability researchers have been chasing for years, we built it inside this new foundation for all future generative models. Because knowledge is stored in non-diffuse local way, adhering to neural selectivity, only task-relevant compartments activate. Only relevant neurons and synapses, aka nodes and weights, load into GPU memory at a time. The entire model, aka the brain, is never required at once. The consequences are dramatic, orders of magnitude lower compute and lower energy, AI that runs where traditional transformers cannot. Traditional models have parameters with fixed size at birth. Ours grow. Neurons and synapses are created only when needed and grow with the amount of data the models feeds on. No fixed parameter count, no catastrophic forgetting, no overwriting old knowledge to learn new. We provide a small controllable set of hyperparameters, and based on these, the model flexibly scales according to the data it feeds on. All in all, this yields unprecedented data efficiency and removes the need for massive duplicated datasets. You may remember the patches from previously which AI companies and researchers introduced to the original transformer to improve generative AI models. Here's the key insight: almost all of them still work in our architecture. Data scaling, model scaling, alignment techniques, mixture of experts, chain of thought fine-tuning, KV reuse, recursive prompting, and Ingram embedding lookup. Our architecture benefits from them all. In fact, they benefit from them more than traditional transformers. Overall, this means the neuromorphic symbolic transformer can scale efficiently across all generative AI projects which are currently powered by its predecessor. This is the end of the road for the traditional transformer. AI companies and the industry as a whole has extracted nearly everything it can from the 9-year-old transformer architecture. Recent gains come from brute force, more data, more compute, more energy. And as leading researchers like Jan LeCun and Ilya Sutskever have warned, scaling alone is no longer enough. You see, every once in a while, progress doesn't come from optimizing harder, it comes from rethinking the design entirely. The car didn't win over the carriage by breeding faster horses. It won by abandoning the carriage design entirely. Our competitors are still optimizing the carriage. We left it behind. Why the others couldn't do this? Because the industry fell into a trap. When transformers showed spectacular results around 2022, the entire industry fixated on a single metric: better generative responses. Everything else, efficiency, energy, interpretability, was treated as secondary. To understand the consequences, consider the following historical lesson. In 18th century Prussia, timber was a hot commodity for the Prussian state, so the state decided to optimize its forests for more timber yields. Natural ecosystems were replaced with neat rows of artificially planted identical trees. At first, it worked beautifully. Timber yields rose and yields prediction stabilized. Then, the forest collapsed. Pests spread, soil died, resilience vanished. What has been stripped away as inefficiency turned out to be the invisible infrastructure that made forests survive long term. This is the classical Goodhart's law. When a measure becomes the target, it ceases to be a good measure. Modern AI optimized for good generative responses and behavior, and sacrificed everything else. We took a different approach. We didn't ask how do we optimize transformers. We asked how can generative intelligence work efficiently. And there's one biological machine refined over millions of years of evolutionary pressures to be the most efficient intelligent machine known to mankind. That's the human brain. So by aligning generative AI with biological principles, we create next-generation AI models that learn faster, reason transparently, scale efficiently, and operate sustainably. This is not a patch. This is a new foundation.
Today, the AI industry looks crowded, noisy, and confusing. AI has become the most powerful marketing word of this decade. But beneath the surface, most companies labeled AI are not actually building AI. The market, once you strip away the hype from it, falls into 4 distinct tiers. The largest group sits at the bottom. These are companies that sell the idea of AI, not the technology. Their products rely on traditional software, manual human labor, and scripted workflows. Many of them appeared or rebranded after 2022 when large language models captured public attention. They are product-first companies with little understanding or ownership of the technology they advertise. Builder.ai is a well-known example of this. These are not AI companies, they are marketing-driven software businesses riding a trend. The second tier is more honest and more capable. These companies genuinely use AI, but they don't build it. They depend on third-party APIs and optimize UX and business models, as well as rely on OpenAI, Anthropic, or similar providers. They are valuable businesses, but they are AI users, not AI creators. And when cost of inference rises or access changes, their foundations shake. Now the field narrows sharply. This tier includes OpenAI, Anthropic, Google DeepMind, Meta, xAI, and DeepSeek, as well as small labs and research startups who build smaller models, as well as agentic systems. These companies build models directly from frontier research. They sit at the top of today's AI hierarchy. But despite their scale and power, they all rely on the same underlying engine, the transformer architecture. They compete with one another by providing different patches to the engine or by scaling and optimizing it. Nevertheless, the engine is unchanged at its core. This is the rarest tier, the source layer. These are companies that invent the tools everyone else depends on. In the past, Google Research played this role, introducing deep convolutional neural networks and the transformer itself. These inventions didn't compete with products, they reshaped the entire industry. We at SilicoSapien operate here. After 5 years of research and development in the field, we developed a successor to the transformer. We call it the Neuromorphic Symbolic Transformer, NST. But more importantly, NST adheres to a broader paradigm known as Neuromorphic Learning, a family of architecture designs built on learning principles inspired by cognitive neuroscience as opposed to brute force optimization. Just as deep learning replaced classical AI, Neuromorphic Learning aims to replace deep learning. Everything we will launch runs on our proprietary engines, no external dependencies, no rented intelligence. Our general-purpose models include ChatSapien, conversational intelligence, PhotoSapien, visual understanding and generation, TeleSapien, speech and audio intelligence, DevSapien, code intelligence and developer tools. Alongside these, we introduce Agentic Sapiens, which are a suite of task-specialized small efficient agentic systems built for enterprise projects and applications. This is intelligence designed to work more efficiently and at substantially lower costs relative to our competitors. Orders of magnitude lower costs relative to our competitors. Our architecture is fundamentally more efficient. That means orders of magnitude lower training costs and orders of magnitude cheaper inference. This allows us to price dramatically below today's market while maintaining stronger margins. Current AI companies are not expensive because of demand, they are expensive because of architectural inefficiency. We removed that bottleneck. Additionally, our most distinguished feature is white box models that are fully interpretable, auditable, and that can be easily debugged. This allows for a level of model control and transparency never achieved before. We operate with intention. Only the simplest architectural concept is publicly disclosed. Core systems remain protected. We learned from history. Open sourcing foundational engines too early benefits competitors more than innovators. This ensures long-term defensibility and protects against rapid replication by foreign entities. We enter the market where friction is lowest and impact is highest. Small, efficient models, agentic systems offering freemium access, as well as paper publications showcasing superiority results across all different benchmarks. We intentionally spend years prioritizing our technology over hype, laying core technological foundations most AI startups don't have. We did this to completely eliminate any R&D risks which promising tech startups tend to combat at later stages. We chose depth over speed and technology over hype. If there was a metaphor to represent our timeline, from 2021 to 2025, we have been pushing a snowball up Mount Everest. In January 2026, we reached the summit. Now, gravity does the rest. Our next period is expansion. The next phase is where the snowball rolls downhill, picking up speed and momentum while growing at an exponential rate. Products launch, adoption accelerates, partnerships form, and scale becomes inevitable. For years, AI companies followed two paths: scale data and compute, and patch the transformer. Everyone raced forward on the same foundation. We didn't. We chose the third path, where we built the foundation itself. In tech history, early solutions have always been less optimal. They always have been inefficient, expensive, and architecturally constrained. And the pattern is clear. Google beat Yahoo, Amazon beat eBay, Facebook beat MySpace, and Chrome beat Netscape. So the first wave is not necessarily the final one. We didn't build to arrive first. We built to last. If there was an AI bubble, and if the market was to correct, when it does, Tier 1 startups will disappear and Tier 2 startups will struggle. Those who own the engine will survive and grow in a post-bubble era. SilicoSapien is not exposed. SilicoSapien is the hedge. The neuromorphic symbolic transformer enables systems that are structurally closest to human-level intelligence and in turn AGI. Not by scale, but by design. We are not building another AI product, we are building the next era of artificial intelligence.